I would like to welcome Abe Radin to the podcast. Thanks for joining, Abe.
Thank you for having me.
So Abe's doing his PhD in math right now. He's in his third year at CUNY Graduate Center. And Abe is one of the smartest people I know. So I invited him on and we're going to talk about math. So, I used to love math. It was actually my favorite subject until 11th grade when I started doing calculus. And then I hated it. And the reason why is because that's when I stopped understanding what it meant. I didn't understand what was going on. Like I was able to do the equations. I was able to do the integrals, the derivatives, and limits. I think limits is when my math career basically ended. It was my favorite subject. And then limits, I really was just like, what is going on here? Like, is it real or is it not? Because I've heard like the concept is like, oh, as something approaches 1 or 0, we act as if it is that number. And I never understood that. So that's when math fell apart for me. So I went into physics. But I want to talk about math.
There's a lot of math in physics.
Yeah, there's a lot of math in physics, unfortunately. That's sort of the problem. I think a lot of physicists do not like math. That's what I've heard. I heard Einstein didn't really love math. He just more used it to help him. Probably not true. I don't know. Probably did like it. But anyway, so I wanted to talk about the foundations of math. And I wanted to ask, is math a discovery or is math a creation? Let me explain a little bit about what that means. So if it's a discovery, that would mean that it always existed. And let's just say, for example, 1 + 1 is 2. Yeah, you have one thing and you take another thing and now you have two things. It's very simple. So simply, that is a discovery because I think that people who were never on this planet, if they were just, there were new creations, these people that think, there were these new thinkers, they would discover the same equation of 1 + 1 is 2. That's what I think. So at first I'm like, okay, this is probably a discovery. It's obviously true. How could you deny it? But then I was like, but math describes the world really well, especially in physics. We use it to describe the things we see. So if it was this thing that has nothing to do with reality and it was just always existed, even before, let's say, the universe existed, so why does it describe the universe so well? So I'm like, so maybe it's a creation that we use for the universe. So that's the two sides in my head. That's how I'm thinking about it. And I want to hear what a mathematician has to say about that.
Yeah, it's a famous question. People have been asking it for a long time. I think those two questions are very related, but possibly different. The question of whether it's a discovery or an invention and whether or why math is so useful to explain the real world. Because math could be so useful to explain the real world, whether or not it's an invention or a discovery. So in a way, they're two separate questions. Whether or not math is an invention or a discovery, I think also comes down to what you think math is. If it's just these statements, 1 + 1 = 2, then okay, I guess that's true objectively, right? And it's just a fact regardless of if you've invented it or discovered it. But the way we write math, our choice, our notation, our assumptions that we put in, that is a choice that we make. Of course, when things are just numbers, 1 + 1 = 2, it seems basic. But a lot of math has theorems, has conditions. If this holds, then this holds, right? You have a lot of calculus. You have these things that seemingly aren't super related that end up being related, like derivatives, integrals. And that is seemingly getting at something that should be true, but without having axioms, without defining your mathematical objects in the first place, what does it even mean to talk about a derivative without defining one? And that definition may require that human to invent that thing in the first place. And that brings to a deeper question of, do these mathematical objects exist in the real world, right? Is there
What do you mean mathematical object?
So a number, a derivative, like something that has a mathematical, flavor to it. Like when I say the number 7, I say a vector space, I say a linear transformation, I say a matrix. Is that a real thing, or is it just something that's getting at like a relationship between two things we already invented? If it is a real thing, if it does actually exist in the real world, if there is the set of real numbers is like a real thing you could point at, maybe not like a physical thing, but I could say
Right,
like
it's
this,
not physical.
right? Non-physical.
It's almost a little bit like spiritual, It's a little bit like God. It's
Yeah,
like
there's.
it's not physical, and it's not in space either,
Right. But there's this idea that like there's like the true, like there's this famous idea from Plato, like the Platonic cup, like is
No,
there
I don't know what that is.
So like do things have like an ideal form that they take? Like okay, you could point at a cup, but is there like a true cup?
A true cup, right.
That exists. I mean, just as like an analogy. So when you think of the number 3, right, you could point to 3 objects, you could talk about like 3 + 1 = 4, but is there like, does 3 exist, right? Like by itself? And, that's like a question that people debate. But I would say if it does exist, then maybe you could speak of like we discover it. But if you say it doesn't exist and that's a human invention, then a lot of math could be invented similarly. But even then, it seems like a lot of the patterns that we discover in math seems like we're getting at a pattern that actually exists. Where it exists, I think, is a good question. But it seems like it does exist. But I think what a lot of people agree to is that the part of math that is invented is our choice of what axioms to take and how to formulate like the math that we do. So like the assumptions that we make.
So I guess like what would be an example of something we invented?
An example of something we invented. Well, the decision to focus on certain mathematical objects, for example, in abstract algebra, a field of math that, most physicists maybe, physics majors wouldn't have seen.
No,
but,
I don't know what you're talking about.
Right. So you define like things, for example, called a group, and a group has certain axioms that it obeys. You could kind of substitute axioms for definitions. Like what is a group? A group is a set of things that has certain properties. That is like an invention. We decided to invent this thing called groups. A lot of things in math are groups, but it was a human decision to go, these things that we noticed all have similar patterns, we're going to call them groups. And what groups are doesn't really matter. I could list 100 different things. It's just like an example. And
so groups are used in math?
Yeah, huge field, group theory.
What's like a most simple example of like a group when it comes to math?
The integers are probably the most basic example of a group.
But like, how is that mathematical? It's just like grouping it. How does that become a mathematical thing?
So a group, just to explain it, is a set of things that has a way of combining 2 elements in that set to get something else in that set. So it's generalizing numbers, right? If I have 3 and 1, I combine them, I could get 4. In a group, I could just, a general group, very abstract, physics, like what's the point of this? But in a general group, I could take 2 things, combine them and get something else. But there's a few other things that needs to hold. One of them is there needs to be an identity element. So when I combine 2 things, but one of them is the identity, it doesn't change the other thing, right? And that's kind of like 0 in the integers. When I add 0 to anything, I left that thing unchanged. Similarly, we have...
So is 0 part of the group of integers?
Yes.
It is.
So I should clarify. The integers are the negative numbers, the positive numbers, and 0.
Okay.
Whereas natural numbers, it's the positive one. Some people debate if 0 should be included as a natural number or not. So you have this identity element in the group. You have inverses. That means if I have an element in the group, there should be another unique element in the group that kind of cancels out that other one. So they combine to the identity. So it would be a reciprocal in the context of multiplication. But with addition, it would be subtraction. So subtraction is that, so what does it mean to subtract if you're like a group theorist? A minus B really just means A plus the additive inverse of B. That's what A minus B. Minus B just means I'm adding this unique inverse. And all of this is like trying to get at.
But what is that? How does that have to do with group theory? So you have a group of integers.
Well, the group of integers is one example of a group.
But in that group, where is math being used? You're saying that there's something called the additive inverse, which is if you add it, you'll get to 0?
The additive inverse, so if A is an element of the group, one of the group axioms, the assumptions, if we're talking about a group or definitions of a group, is that there'll be another element in my group that I could call the inverse of A. That when I combine it with A, I get back the identity element. So every group has an identity element. If you're talking about the integers, you could just think of it as 0. but other groups may not be numbers, right?
Uh-huh.
Groups are trying to generalize some
Right.
ideas
So
of numbers.
yeah, I did a little bit of this in linear algebra. So
So linear algebra is the study of vector spaces and linear transformations on those vector spaces or matrices. A matrix is a linear transformation of a vector space, and a vector space is a group. I could add two vectors, I get a vector. I could take a vector and subtract a vector, so there's inverses. The zero vector is always in there, so I have the identity element. And it's closed. If I add two vectors, I always get another vector in that vector space. That's the closure property. So
there's different properties to these groups.
there's like four defining properties, and I kind of mentioned all of them. There's one other that I didn't mention. It's usually like ignored, but it's the associative identity, which is that A composed with B, C is the same as AB and then C. So I could kind of like reorder things.
Oh, like A plus B plus C is the same thing as, well,
A plus
same thing
B
as
plus
B.
C is the same as A plus B plus C.
right.
That's not true for all operations, like subtraction, for example, or but
Right.
usually you have associativity. That's not the same as saying A times B equals B times A. That's true with integer multiplication and integer addition. But for example, matrix multiplication, if you remember from linear algebra, it's not true that if I have two matrices A and B, that A times B is B times A.
Right.
So sometimes
matrices is different.
Yeah, that's not a fundamental property of multiplication, that the order doesn't matter.
Right. Okay.
But so the reason I brought up groups is just to give an example of groups have a lot of rich properties. They have only a few axioms, and we could say a lot about them. There's like deep theorems when it comes to groups. There's entire textbooks dedicated to group theory, and some like really useful theorems that have been about things that you wouldn't think are groups. Like one of my favorite ones is just historically that if you remember back from high school, you learned the quadratic formula.
Yeah.
Well, it turns out there is a cubic
I
formula.
do not remember it.
No?
No,
I'm
not
sure
too
you
useful.
do if you really
No,
search your
I
brain.
have
Really?
I do not remember it. No.
People have songs, I guess, to help them remember.
Really? No.
So there's famously
I don't know. I in physics, we don't really memorize formulas. We get all the formulas on the test,
That's
and
fair.
then the question is which one are we supposed to use?
I feel like people who weren't even math majors and physics majors remember it just because of how often they had to use it in high school.
Oh, really?
But yeah, there's also, so things that people don't learn are that there's a cubic formula and a quartic formula, which is formulas for solving cubic and quartic equations. So degree 3 and degree 4. They're extremely long. The quartic equation would take you like a page to write out.
Wow.
I don't know if there's a single human alive that like
That
even
knows
knows.
it by heart.
I don't even know if any, it's insanely long. But the deep thing is that once you get to 5th degree polynomials and higher, there's no possible formula. It's not that we haven't found one yet. It's provably impossible
Really?
to write down a formula.
That's so
And
cool.
to be technical, that means there's no way of writing that formula using like plus, times, and division and taking radicals. There's obviously
There's
solutions.
other ways.
Not that there's other ways, but there are solutions to 5th degree polynomials, but you won't be able to write them in your normal
In your
like-
normal form.
So that is like an application of group theory, something called Galois theory, a little bit more advanced than group theory. And this is going back to almost like when group theory started. And this is like an application, but the point was that group theory is like an invention in that our decision to call this thing a group, to collect these random properties that a lot of things have, and to say like this is going to be the thing that we study for groups, and for many other mathematical structures doesn't need to be groups. But that was a human decision. Like groups don't exist in the universe as like a list of definitions.
Right.
All of these objects exist in some sense, but we get to decide what we want to call a group and study that. But I would say the things that follow from the definition, they truly exist. The implications, saying that something has property 1, 2, and 3 implies some other thing, that's true. Like that just exists in the universe. But you deciding to define that
reasoning
thing,
is true.
Yeah.
But the definitions of the groups themselves are just human choice.
Yes.
Right. So meaning the way to classify like 0 to 100 and all the negative numbers as integers, not to 100, to infinity, whatever. Basically, all the whole numbers, to classify them as integers, as this group, that was a human decision. And I guess the properties of a group are also human decisions, like that you have to have like an identity.
The identity elements.
Right. So those things
the
are
inverses, associativity, closure. Right. Yeah. Those are all like, we decided to define it that way. But in theory, you could have defined things differently. And the point is we do define things differently. There's something called rings and monoids and semi-algebras or semigroups and modules and fields. And I mean, you may have seen fields in vector spaces. So the whole study of abstract algebra is really defining these like different mathematical sets that have different properties and seeing what follows from them. It's our decision to like define a field, to define a vector space. But what follows after those definitions, like there was no decision, right? Once, I mean, I had a professor in Brooklyn College who said like all of math is the definitions, the rest is commentary. And you know, in some sense, I don't agree because like really doing the math is actually doing those implications, is doing the steps.
That's pretty hard also.
Yeah. But I think the point was once you define things a certain way, there's no other things that it could be. Like once it has a set definition, all the facts about it follow from the definition. You should be able to prove everything possible about a thing in math from its definitions and your assumptions.
Right.
You shouldn't need to like pull something like from somewhere else. I mean, sometimes we use like other theorems in other fields, but.
So I guess to summarize, you're saying that it's both a creation and a discovery, and it depends which part we're talking about.
Yeah, I mean, I guess that's a bit of a cop-out answer, but.
Yeah, right? Interesting.
It's hard to settle on just one, really.
Right. Yeah. I guess, you know, like before I asked this question, I was thinking, you know, maybe it's just a matter of semantics. But after hearing your answer, I think it's not anymore because there really is a difference between, let's just say if 1 + 1 is 2, then, you know, 2 + 1 is 3. I don't know if that follows. I think it does. Yeah. So like versus deciding to call a group of integers a group.
Right.
You know, and making all these different properties. So
but it's also your decision what plus means. Like if you like, maybe that's a different operation that does something else with 1 and 1. Right? So it's like,
that's a matter of semantics. Like what does plus mean? That's a semantic question, no? But in terms of like the concept of like taking two things and putting them together.
No, yeah. So
that's not a matter of semantics.
I would say it's still a bit of a semantics because what does putting together mean? Like there's different ways. I mean, you see this more in like different fields of math.
But the truth is two is just a group of two things.
There is a group of two things, but it's...
So at the end of the day, maybe it is all just groups. I mean, I don't know. I don't know about that one. Now I'm a little confused.
Well, I guess the thing that I was trying to say is like, for example, you could have two functions and there's different ways of multiplying functions. So you say like plus is just combining, but combining is vague. How do you want to combine something? Okay, addition is kind of simple, but there's ways of combining things. For example, I want to multiply two functions. Okay, you might just think to multiply them, like take a function, take its output and multiply them. But there's other forms of multiplication. There's something called like an inner product and you have these functional spaces.
Yeah, like let's just say multiplying matrices. There's a formula that I learned for that.
Yep.
So I guess let's just say that. Would you say that's a creation or would you say that's like fundamental discovery?
I would say the definition of multiplying matrices is...
Is it like a different definition than multiplying numbers?
It's an invention, but it follows from trying to get at what multiplication of... Really, you have something that you want it to do, and you define something to obey the thing you want it to do. So the multiplication of matrices really is supposed to capture the composition of linear transformations. So every matrix corresponds to a linear transformation between vector spaces, which, you know, like you'd have to like write down and like see how that works. You would, I don't know if you're familiar with like,
no,
you have a basis.
I'm not familiar so much with this.
Right. So you have these things called linear transformations between vector spaces. And for each, so you could think of a linear transformation as a function from one vector space to another that has a certain property. We don't have to worry about what that is for right now. And the idea is that, okay, I have a function from one vector space to one, and I have another one, and each of those could be associated to a matrix. And the idea is that matrix multiplication is associated to doing one of those linear transformations one at a time. So I first do one and then do the other. So that's going from multiplication to composition of functions. And if you remember from like high school, composition of functions is you first do one function on the input and then you apply the second function to it. But that's not multiplication. That's doing f and then doing g, right? F of g, or first doing g and then doing f. Whereas matrix multiplication is, it's just a multiplication of matrices. So there's this connection between those things. And that's kind of what I was trying to get. When you say you're combining two things, that's vague. Like even addition, maybe when I'm combining 2 and 3, I really mean 6. How do I, like, the choice of combination is really...
Well, how could... Oh, you're saying because you might mean multiplying like 2 and 3?
You might mean multiplying. Maybe there's a third operation. Maybe it's 2 to the 3 and you get 8, right? So it's like... It depends what you want like your operation to get at. We care about addition because we physically combine things all the time. But like mathematically, it's not clear that you just give me 2 things and the thing I want to do with them is add them.
Interesting. So here's a question, okay? So let's just say, there are certain deductions you can make in math once you have the rules, I guess. So are the rules invented?
If by
And by, I guess by rules, let's just say, for example, 3 plus x equals 5. Okay, so how do you solve for x? You do 5 minus 3 and you get x. So is that rule of like, how do you get x? That rule is created by us or discovered by us?
So I think like that kind of algorithm, that step-by-step process to like solve for x, I don't know if I'd call it like an invention, or I mean, it's kind of an invention as like a method. But the idea that x actually equals, what did you say?
2.
3 plus
3 plus x is 5. So
right.
x is 2.
So x is 2. In that sense, I think it's just true, right? But if you like change your mathematical setting, it could be different. So it really depends on like what assumptions are there. But yeah, like if you don't.
What do you mean if you change your mathematical setting? How could it be false that you just solve it by just subtracting both sides?
So that should work. But I guess I mean if like plus means something differently to you.
Right.
Or if,
right. But we know what plus means and we know what equals means.
Right. But like what if you're, I mean, just to be annoying about it, right? Like if you are dealing with matrices, right? You could scale matrices by a number. So what if it's 3x, what was it? 3x plus
3 plus x is 5.
3 plus x equals 5. Maybe I'm thinking that 3 and 5 represent like the identity matrix times 3. So maybe I'm looking for a matrix instead of a number, right? Or if you're familiar with modular arithmetic, maybe it's
right,
3
but that
plus,
would be dealing with a whole different situation.
right, that's what I'm saying. Like if you change the setting, but if you're just dealing with like normal numbers.
By the way, for those who don't know, a matrix is basically like numbers that I guess go the, like, let's just say you have, how would you define a matrix?
I would think of it as like a grid of numbers.
A grid of numbers. Okay. So you're multiplying grids of numbers, if that makes any sense.
Yeah, it's a simple explanation.
Yeah. So that would be, you could also add grids of numbers. So yeah, just in case you didn't know.
Well, so for example, if I asked you what 5 plus 7 is, what would you say?
I would say 12.
You would say 12. But if I'm on a clock, I might say 0 because it gets back at 0. Right. If I ask what 6 hours plus 7 hours is,
1
it might just be 1, right?
Right.
So this, like, it's in that sense that I think like the setting matters. And yeah, if like we agree on the setting, I think it's like obvious like what certain mathematical questions should be. You still kind of, you know, if you really care about like foundations of math and being all theoretical and pure about it, you'd want to prove these things very carefully and rigorously. But it's not like people did that like 2,000 years ago. They were able to solve math. It's not like the Greeks, like they did plenty of math without like discovering set theory. And
right.
So
yeah. Mm-hmm. So I guess to summarize, are we sticking with it? That part of it is a creation, part of it's a discovery?
To me it is.
To you it is. Okay. I mean, I'll tell you the truth, now I'm a little confused. At first I was leaning towards the side like it's for sure just a discovery. With groups, you're right that it seems like it's a creation. I just got a little confused because 3 is technically a group of 3 ones.
When I say a group, I don't just mean like a group is a specific mathematical structure that has certain properties. It's not, so what you're thinking when you just say a group of 3 things, that's what a mathematician would call a set. A set is very general. It's just a way of collecting things. So I could say the set of 3 things. I could say the set of cat, dog, and something else, right? You could collect anything into a set. A group is a set that has certain properties to it. So you can't just say the group of 3 things. There is a group of 3 objects, and it's a unique group, which is, you know, if I have like the group of 20 things, there's many groups that you could have of 20 things. But because 3 is a prime number, there's only, it's a random fact. But yeah, so I just wanted to make that distinction.
Okay.
But I think the problem with saying math is just a discovery would then beg the question, okay, you're discovering something. What is it? You have to like point to it. You discovered something. What did you discover?
I don't know if you have to point to it. You can't discover something that is existing in, I guess, a different type of existence. Than
well, that's kind of the thing I was getting at with like the Platonic.
Right.
Like, is there some like universe, either
it's
a
like
universe
a different dimension, or maybe it's just metaphysical, you want to call it, something like that.
I think if you believe in that, then sure, I could grant that. Like if you believe in a universe where...
Well, I believe in it because of math. Okay, is that possible? That math proves that there is something not physical that exists?
I don't think math proves...
Because think about it. How else are we discovering this thing? We're just making it up. We're getting to truth.
That's what the invention perspective would get at, that all math is made up. it's still getting at something. It's getting at like the patterns
But
that we see.
but it works. But it works.
But I would say that's a different question. That's like, to me, it's a more complicated question, just because like I don't know any physics, and it's like hard for me to imagine like why the universe has like such built-in, symmetry and math properties, like F equals ma. Like, okay, but how does the universe know to do F equals ma? How does it know that when I throw a ball to
well, it's
calculate
more that
it?
we saw the universe and we figured that out. But I guess, why is the universe in such a way that we can mathematically describe it so easily?
Yeah.
With such simple equations. I mean, electricity and magnetism, at the end of the day, I think you can sum it up all in like 4 Maxwell's equations.
Right.
So I think when it comes to quantum mechanics, that's when things get, a little bit more complicated, and things, that's why Einstein was so upset with quantum mechanics, was because the world was supposed to be beautifully simple.
Right.
And that's what he tried to do with, general and special relativity. He tried to combine a lot of different things into one, and then he failed when it came to quantum mechanics, and that's why he didn't like it. But right, math does work. So it's you can really look at it 2 ways. It works because we discovered the truth, or it works because we saw the world and we invented it to make it work. So,
but even if we only invented it to make it work, I still think there'd be a question like, why does the universe seemingly follow such nice patterns? Even if it has nothing to do with those patterns, maybe those patterns were just an invention of ours to model like the universe. Why is there such like a
why is there even a pattern to even notice?
Yeah, why is there even a pattern to notice?
Yeah.
Or maybe that's like the wrong question to ask, because it's only a pattern we notice because it exists. Maybe like we're biased in thinking some things are nice because we happen to like see them as patterns.
Yeah, but so it could have existed a different way.
But maybe then we would have seen that as a pattern, right? So like no matter how it existed, like I think the real question is, why is it even something that could be mathematically formulated? Like why like F equals ma? Like in theory, like the universe could just do what it does, and there doesn't need to be any math or equations. Well,
that's sort of quantum mechanics. It's like there is no rule that it follows. It's just probabilities.
Well, probability is a very deep field of math.
Though, yeah. So I guess even that does follow rules. Yeah. So just to take this on to a further topic, a different topic, but somehow connected, infinity. Okay. So now infinity, would you say that infinity can exist? So it does have a little bit to do with creation versus discovery, because we use infinity in math. But is it actually something that can exist in reality?
Mm-hmm. So I think it also depends what you mean by infinity. I think the first instance,
an infinite number of apples, can they exist?
So
the hotel room paradox, like
Hilbert's hotel.
Yeah, I don't remember exactly. Could you explain what that is?
Imagine someone shows up to a hotel and it has infinitely many rooms and they're all full, and they ask for a room and they're like, well, the rooms are all full. What could they do to make room for this person? Okay, pretty easy.
Well, how could it all be full? It's infinite.
Okay, but there's infinitely many people.
Good.
For every
Okay, nice.
For every room, there's someone staying by it. So then someone shows up, and what do they do to make room? They just put person in room 1 to room 2, person in room 2 moves to room 3, and you just move everybody. It's a huge inconvenience to the infinitely many people, but okay, there's a mathematical way of doing it. And then you could take this further and further and say, what if an infinite amount of people shows up to the hotel and the hotel's full? How do you make room for infinitely new people to the hotel? Well, the answer is just move
everyone infinity over.
Well, what would infinity over means? You have to tell person 1 where he's supposed to go. So you can't just say go to the infinite room. There's no infinite room, right? There's in the same way there's infinitely many natural numbers, there's infinitely many rooms. But in the same way that every individual natural number is a number, right? There's no infinite number, but there's infinitely many numbers, right? Which is a little bit of a distinction. So I would tell person in room 1 to go to room 2. I would tell person in room 2 to go to not room 3. Nope. Because that just, I only then opened up room 1. I tell person in room 2 to go to room 4. Person in room 3 goes to room 6. So now after doing this process, all of the even rooms are still full, but I just opened up infinitely many rooms because every odd room is now empty.
Oh, that's wild.
Right. And that's kind of getting at, famous.
Wait, but room 4 is also open, no? You told room 3 to move to room 6?
No, because person in room 2 went to room 4.
Oh.
So every even room. So if you have an even number.
Oh, right.
If you have an even number 2n, person from room n went to room 2n.
Okay.
but there's no person in any odd number rooms.
Oh, nice. Okay.
But you can make it even more complicated by
That's
saying,
genius. Whoever thought of that.
yeah, but if you have, so there's different types of infinities, which could be a whole other discussion in and of itself, but I think it's really interesting. But if you had like a much bigger infinity of people showing up to the hotel, and you only had like a smaller type of infinity amount of rooms, there'd be no way of, even if you emptied out the entire hotel, there's no way of fitting this like greater infinity into the room. But whatever, that's
right. So this seems, I mean, this idea does seem, I guess, impossible.
So it depends what you mean. Like physically, obviously, I don't believe such a hotel could exist. But if, as an analogy, you mean like a set of natural numbers, and I ask, is there a way to fit the even number? Like if I'm talking about even and odd numbers, like in the hotel, and I say, okay, what if I want to like move some numbers into other numbers and talk about them as sets? Then if you do believe like these sets actually exist, back to the previous conversation, like if you think the set of natural numbers actually exists, so maybe it doesn't exist in the physical world, but like in this meta, universe where like numbers exist,
hotels,
then like why can't like infinite objects exist? Right. Physically, I would agree. Right. I mean, the universe might be infinite, but that doesn't mean an infinite. I mean, you could consider the entire universe an infinite hotel, possibly.
What I mean, what is the current, I guess, consensus about like the universe? Is space itself infinite, or is it finite? Like the universe, just
I'm not a physicist, but I think
yeah, I'm asking you the physics question.
I might not be the right person to ask, but I do think I think it has to do with things that I've seen about like what we think the curvature of the universe is. So I think if like the curvature is 0, then we would expect
it's flat,
kind of like flatness, yeah. Then we would expect the universe to like be infinite. There's no reason we would like expect there to be like an edge or a boundary or something bounding the universe. But if there is some kind of curvature to the universe, then in some way you could think of it like wrapping around on itself.
Like a circle.
Like a circle, or like, more in like higher dimensions than a circle. But
yeah, because even a flat universe doesn't make sense because like, we're a sphere and we're in the universe. So obviously it's not flat. When I say flat, I don't mean flat like paper flat.
Right.
I mean
3D flat.
Yeah, 3D flat, whatever that means. I don't really know what it means.
There's a whole field of math called differential geometry where curvature and flatness is defined more formally.
Right.
And if something is like Euclidean, you could have Euclidean meaning it's like r to the n, where that represents like n-dimensional space. So like we live in r to the 3, three-dimensional space. R to the 2 would be like a flat plane.
Right. Okay. So I guess, do you think in this, so we agree that, so we think it is, if the universe itself is infinite, let's just say, could this hotel exist? Is the universe this hotel?
It could be.
It could be. So you think it's possible that the universe itself goes on forever?
I mean, if it does.
Would that mean there's like an infinite amount of stars?
So, I mean, I guess that would depend on like the mass, right? In theory, maybe space, like, again, I'm not a physicist. There could be like known answers to these questions, but like in theory, I can imagine a universe that has.
In theory, I'm talking about in theory.
Right, in theory. Like this is a mathematical question to me. I don't actually care what like physics actually says.
Yeah, I don't.
But in theory, I can imagine.
Because even if they say something, I don't know if they know for sure. There's no way.
Or even if they do know for sure. I mean, like to me, as a mathematician, I would care more about like the theoretical, like, so I could imagine a universe that is infinite in space, but has finite mass, right? Like let's say there's like a certain point where like mass gets either dispersed, like at some point you have to travel an insanely farther and farther out to like see another speck of dust, right? And maybe at some point there are no more stars, so it could be like the stars are bounded in some finite region, and then afterwards universe still goes on, but it's kind of like empty space.
That'd be pretty cool.
Yeah, I guess that could exist. But if we assume like an equal distribution of mass throughout the universe, then if the universe is infinite spatially, it should be infinite in mass, and then I would expect like stars, planets, galaxies to keep going out forever.
Right. So to continue on infinity, this was a thought I had about infinity, and I want to know what a mathematician's take on this thought would be. So imagine that the universe is infinite in a different sense. It's infinite in time. So it was always there, I guess you could say, like
in both directions.
In both directions.
Because you could have infinite in time going one way.
Yeah, let's just say it's in both directions. So it always was here and it always will be. Now, let's just say there's certain probabilities for certain events happening. So for example, the probability that me and you are going to come back here and do the exact same episode tomorrow, very low, unlikely. but possible, not impossible. If there's an infinite amount of time for things to happen, and these things have low probabilities, but it doesn't matter, does that mean that, like, how would, I guess, you deal with a extremely low probability of something that has an infinite amount of opportunities to happen? So if you say that, well, there's an infinite amount of opportunities for it to happen, so it's gonna happen, well, then does that mean everything that could have happened already happened? Which is a crazy thought. It doesn't mean yeah, it seems impossible. It seems like ridiculous. So, but mathematically, I was just thinking about it. How do you deal with low probabilities with infinite opportunities?
Yeah, that's a great question. I think that if something has any number of probability that's positive, meaning like not zero, it could be like insanely small, 0.000001, you would expect it to happen at some point. I mean, you could think, yeah, I mean, I think a good analogy would be like flipping a coin, right? If you flip a coin and you get some like sequence 100, like you flip a coin 100 times, you see heads, tails, tails, head.
Yeah.
The probability that that happened is, if you look back before you flip those coins, insanely low, but it just happened.
I just want to clarify just for the audience. What he means is not that that it will get heads or tails. You mean that it will be the exact order that you flipped it 100 times, right? That's what you're referring to.
Well,
meaning you flip it 100 times. First time is heads, second time is tails, third time is tails, fourth time is heads. Like that order of 100 times,
yes,
that order of it happening that way is extremely low.
It's extremely low, but I just did it.
It's whatever, what is it? It's 1 over 2 to the power of 100.
Which is an insanely large number. And you could
like how big are we talking? What's 2 to the 100? I don't know.
I don't know exactly, but if you just replace 2 with 10, obviously that's like a bad approximation, but 1 over 10 to the 100 would be 0.010, like, sorry, 100 zeros and then a 1. Now, 2 to the 100 is a little bit different because that's 2 and not 10, but like they're not like too far off.
But it could be at least like 50 zeros, 0.0 with
easily.
50 zeros.
And I could flip more coins, right? You want to make the number as small as possible. You could do an event at any time that has an insanely low probability of happening, but you don't think of probabilities after the fact, right? Like anything that happens has an extremely low, like the exact arrangement of it has an insanely low probability. You need to ask beforehand. If I ask beforehand, what's the probability of flipping this like exact sequence of coins, and you do it, that would be really surprising. But flipping a sequence of coins and then saying what was the probability of that extremely low. So all this is to say is that if I was flipping coins for an infinite amount of time, I would expect any arrangement of heads and tails to eventually show up.
It would show up.
Yeah. In fact, it wouldn't just show up. It would
show up an infinite amount of times.
It would show up more times. Like you wouldn't be able to bound the amount of times it shows up. I don't know if it makes sense to say it would show up an infinite amount of times, but there'd be.
Why not? Why can't you say it would show up an infinite amount of times?
Well, it depends on like the rate at which you're going back. Like, yeah, if you're saying like the probability that this thing, what does it mean for something to show up like an infinite amount of times?
For it to show up an infinite amount of times, it happened over and over and over and over again.
Right. Okay. So then, yeah, like you would expect that to happen.
You would.
But you have to be a little bit careful when things go to infinity. But I think one thing I'm confident in is that it wouldn't make sense to say I only expect it to happen 5 times. Like, why not 6? Like, there would always be another time that you would expect it to happen.
Right. So I guess that's like another problem with, let's say, infinity actually existing, is that you would basically have to say that everything that could have happened, which would mean that I existed already. You know, somebody exactly like me.
Is that a problem if the universe is truly infinite?
It just doesn't make sense. I don't know. I think there's no way that's true. It just can't be. I think maybe logically it could be, but I can't imagine it. It doesn't make any sense.
Could I make the question even weirder? If the universe is infinite in space and mass, then forget infinite time. Even if the universe is only however old you think it is, then by being infinite in space, I would expect another one of you to exist.
Oh my God, somewhere else.
Yeah, because if there's infinite amount of planets and galaxies being formed, like truly infinite, then like why wouldn't the exact patterns that led to
If
this
infinite
exact conversation
mass.
happen somewhere else in the universe.
If there's infinite mass.
If there's infinite mass, and like
Right.
we assume like things happen like with equal likelihood across the universe, which may not be the case. Maybe physics is different somewhere else, and like we wouldn't even form halfway. But if we assume,
Probably it does.
Yeah, probably it does, right?
Einstein thought it did.
So like if we make those basic assumptions, then I think an infinite universe also implies like these crazy examples, and you don't need to even
That
believe
is
in infinite
crazy,
time.
right.
But the same way you didn't believe it there, like you didn't believe that there could have been a you in the past.
Right.
But then would you refuse to believe that there's a you like a trillion, quadrillion light years away? I mean, the numbers probably get so insanely large, it may as well not exist. Like at a certain point, how far away does something need to be
Right.
for it to even not exist? But like, yeah, let's just say there's a big enough number out.
And then you would say there's an infinite amount of me's.
Yeah.
Right. Yeah, it can't be.
Why would it?
That probably also can't be.
But then you must necessarily believe something either weird about probability, or you believe the universe must be like finite.
Yeah, so I'm gonna go with the universe must be finite. That's it. It just can't be. I'll tell you. But also, the reason why I asked the question is because when a lot of people, they prove God's existence because they look at the design of the universe and they say like, "Wow, what are the odds of this happening?" It just can't be that something so unlikely of like humans forming, from randomness. There's a human mind, things, and I guess how life developed. It's just too crazy to imagine that it happened by chance. So I asked, maybe if the universe is infinite, it does make sense why it happened. People say evolution is lucky, but maybe we got lucky because we had so many chances to get lucky. So that's why I asked the question.
And those chances don't need to be in time; they could be in space, as like I'm trying to get at, right? Even if the universe wasn't around for so long, like if you have an infinite universe, at some point, anything that has a positive probability is going to happen.
So I guess, yeah. So I guess people that think that, oh, you can prove God's existence very easily, just look at the world. You would answer back to that, well, at least one of the answers. I'm not going to say this is the only answer, but the answer, one of the answers to be that, well, like maybe we just had a lot of opportunities, infinite. It would be a lot. It would have to be really a lot for it to happen by chance.
And that's just to say that the thing, I would expect it to happen. Maybe not here specifically, but as long as I have a lot of chances, I would actually expect that thing to happen. But even if I wouldn't expect that thing to happen, we have to be careful and say, and not say that we could conclude things definitively because of low probabilities. I mean, you winning the lottery doesn't mean that like you have some special powers, right? Unlikely things also
always happen. Yeah. Yeah, for sure. For sure. But let's just say when you have a lottery, I would say that like there has to be someone who's unlikely to win.
But what is the probability that I won the lottery?
That's
right?
Low.
So it's similar to Earth.
Whoever it's going to be is going to be low.
Exactly. So what's the probability that Earth developed life, or that Earth has all the things going for it? That might be low. But what's the probability that there is a planet in the universe that produces life? That should be a very high probability. Given,
you think so?
Well, given an infinite.
If it's infinite.
Sure.
Yeah.
I mean,
if it's not infinite.
People believe this so much so that there's like the famous Fermi paradox, which I don't know
what that is.
The Fermi paradox is like, given everything we know about life and how big the universe is and how many planets there are, which fun fact, we didn't even like have evidence of exoplanets, which are planets outside the solar system, till like fairly recently. Like
really?
Stars, yeah, you could like use a telescope and see stars, but seeing planets outside the solar system is not easy. Even now we see them by seeing how they get like in the way of like other stars and things like that.
I didn't know that.
Yeah. So, but like now we know, I mean, we always knew, but like now we definitively know that there are a ton of planets just in our galaxy. So even if the probability of life is like low, the Fermi paradox is like, we should expect a ton of life to be in the universe. Like, why are we? Yeah, because even if it's a low probability, you're multiplying a low probability by like an insanely large number. And is the probability really as low?
I guess, yeah. Well, I would then if what you're saying is true, I think what we need to do is figure out what is the actual probability of the Earth forming and how many planets are out there.
What do you mean the Earth forming?
Like for a planet forming that has the ability for life?
Well, we don't. Yeah, I mean,
and
what
a
lot of people
how
think,
many planets are out there? How many chances would we have?
I think we have like a good idea of how many planets are out there from just like estimates, and like we have a relative range for how many stars. I don't know the exact number. I think it's probably in like the quadrillions for just the galaxy.
Oh wow!
Based on like you multiply the amount of stars by the amount of planets we expect each star to have.
Interesting. Oh, so you're saying you don't even need necessarily an infinite universe to use this argument?
No.
Oh, I never thought
any
of that.
big enough number will give you, I mean, it will never tell you anything 100% if you give me like an insanely large amount of opportunities, even to like flip coins, right? If I flip coins, there's always a possibility that even if I flip heads and tails a quadrillion times, like there's an insanely small chance that I flip heads and never flip a tails, right? That's never going to happen if I flipped infinitely many coins. But there's always an insanely tiny, close to zero probability. So yeah, we can't conclude definitively that just from large numbers that these low probability things happen. But we could say confidently that if you give me enough chances, eventually unlikely events are going to happen.
Right. Okay, so I think we've exhausted the infinity topic. Let's move on to something I've been wondering since high school when I first learned about imaginary numbers. So it is in the same theme of the day of real. Are numbers real or not? Did we create them or not? So like infinity, I would say, if you believe that it cannot exist, it would be probably, the truth is, even if it cannot exist, it could still be a real thing. So I don't know if its existence in the physical world necessarily negates the possibility of it being real. So I want to talk about imaginary numbers. So this is the square root of -1, correct?
I would more like to think of it as when I square it, I get -1.
Okay. So what is, I mean, I always like it was the simplest person in class raises their hand and they say, what are we doing here? Like, why are we using imaginary numbers? It sounds crazy. We have enough numbers, you know? Why do we need something fake? Yeah, so we're just creating imaginary numbers. That has to be a creation, no?
I think they're badly named. I don't think of them as imaginary, and I think a lot of mathematicians who deal with them don't think of them as any less real than the real numbers.
Well, how could it ever be used? It's fake. Well, its name is fake.
That's a great question.
And how long has it been around for? Do you know?
I think like they were formally started using by when they were trying to solve the cubic equation.
When was that? Like,
I want to say around the 1700s.
Oh, pretty recently. Not like
no,
from the
they're
Greeks.
They're not super old. No.
Okay.
Yeah. But I think like, okay, when you say like these numbers are fake, like what does it mean for a number to be real? What does it mean? Like this is part of like the conversation we were already having. But even besides, like I'll go into an area of math that I don't know as much about, or physics, right? In physics, imaginary numbers show up all the time.
They do.
And
yeah.
I know from like the little bit I know there, like often, well, especially when you study complex analysis and you're dealing with imaginary numbers, one easy introduction to imaginary numbers or complex numbers is not thinking of them as a new number system. It's thinking of them as just two-dimensional numbers. So you have X and Y, right? You have your points on the horizontal grid, you have points on the vertical grid.
Yeah.
Now points are going to be anywhere in 2D space. That's going to be a number. I'm redefining number. You're
redefining what a number means.
Well, I'm saying that in this context, I'm talking about a number that has a horizontal component and a vertical component.
You're basically saying a coordinate.
A coordinate, exactly.
Okay.
And one of the easiest ways of thinking about complex numbers, and I say complex instead of imaginary, because no one actually cares about imaginary numbers. What we care about is complex numbers. Complex numbers have a real part and imaginary part. So if you've ever heard of A plus BI,
yeah,
A is a real number.
All the time. I have no idea what the hell it means.
So no one studies just imaginary numbers. What we study are complex numbers. They have the real part and the imaginary parts. But that's the thing we care about. And
we care about what? The real part?
No, both.
No, both. Oh, both. But only when it's connected to a real part.
Well, you could study, like an imaginary number to me is just a complex number where the A is 0. 0 plus BI is BI. It's an imaginary number.
Right, but why are you bringing in coordinates? What does that have to do with this?
So every complex number of the form A plus BI, I could associate it with a point A comma B. You give me a complex number, A plus BI, I'll tell you where on the coordinate grid it is. AB. So it's a way of doing mathematics on R2 or the real plane. I could just associate complex numbers with, okay, but then why do I need imaginary? Like, what do I need the I squared equals -1? That property is going to be, so when you add complex numbers, if I do A plus BI plus C plus DI, you add the real parts, you add the imaginary parts. That's the same as just adding vectors in R2. If you remember your linear algebra, there's no difference. There's nothing imaginary. There's nothing complex about that.
Wait. You lost me a little bit.
Yeah.
I'm confused now. Let's just say we're talking about a coordinate system. Okay. Yeah. So it has an X and a Y.
Yeah.
Right.
So if I have 2 points,
right,
I have an X, Y, and give me 2 other letters, A, B, right?
Right.
there's a way of adding points on the plane as
Right.
vectors. If you remember vectors
Yes.
in physics, linear
Yeah,
algebra.
that I know.
So xy plus ab could be x plus a, comma, y plus b.
Right.
That's exactly how complex addition works. There's nothing special about complex addition. It's just
What's complex addition?
adding complex numbers. When I say complex addition, I meant the addition of complex numbers. So for
And a
example,
complex number is anything that has an I in it.
an I and a real part, or
Right.
just one of them, or every real number is also a complex number where the
Okay.
b is 0.
Uh-huh.
So for example, if I want to add 3 plus 5i to 7 plus 5i, I'd get 10 plus 10i. I combine
Right.
the 3s and the 7s and the 5 and the 5s, right? So there's nothing special about complex addition. Where the imaginary part comes in is for multiplication. So when I add, let's think about adding.
So what does I mean at this point? It's just nothing?
Okay, great question. What is I? I think of I as the point on the graph that goes one up. The real numbers, the A is the horizontal part of the graph.
Okay.
The I part of the graph, the imaginary part, is the
the
vertical.
y-axis?
The y-axis. So 3i is just going 3 up. 5 plus 3i is going 5 to the right and then 3 up, right? So I could associate every complex number with a point on the xy graph. So
Right.
I is just the point. If you know graphing, it's 0, 1.
Uh-huh. So I is just the y-axis. You're just replacing y with I.
Well, that's the geometry. Like we didn't at all get at what I squared equals -1 has to do.
Yeah. Okay.
Right? Like that's next. So when I want to multiply complex,
At this point, I'm just assuming you just decided to make I the y-axis. That's how I'm understanding
but that's
it.
like, okay, why call it I?
Yeah.
And also fine, I
good,
could
good
call
question.
it I.
I have no
but
idea.
like that has nothing to do with I squared equals -1. That's like
Right.
defining property of imaginary
Right.
numbers. Haven't gotten there yet. So complex numbers have the property, many properties, but like one of them that I'm trying to get at in this is that when I multiply, okay, let's just think of like multiplying 3 times 5 is 15. So when I multiply something on the real axis, it's just normal multiplication. There's nothing new. Multiplying real numbers is just multiplication. What the new thing comes from multiplying something on the vertical, right? If I take I times I, what's happening there? Like visually, I have I, it's like going up 1.
Up 1.
And what is I squared? It's -1.
Right.
But where's -1? It's the
Down.
left.
Down 1.
No.
Wait, -1.
Minus I is down 1. -1 is to the left. So multiplication by I is rotation by 90 degrees, counterclockwise.
Interesting.
So when you multiply by I, it's a rotation. So really,
When you multiply by I, it goes into the different, it basically takes the coordinate and puts it in a different, like it's switching from the Y to the X.
yes, but also signs could change.
Right. Yeah.
Yeah. So
you're viewing it as a rotation.
yeah. So instead of thinking as like the square root of -1 and what are these numbers, they are two-dimensional numbers. They exist on like in two-dimensional space where multiplication by the imaginary part is a rotation. And then through something called linearity, or really the distributive property. If you remember, A times B plus C is AB plus AC.
Yeah.
So we want complex numbers to have the distributive property, and that defines how we multiply a general complex number by another one. So for example, if I have A plus BI times C plus DI, I want everything to distribute. But the real like new thing about multiplying complex numbers is the rotation. So if I take, for example, if I have 3, right, and I multiply it by I, it becomes 3i. It's just rotating 90 degrees. And if I have like some random complex number, 3 plus 5i, it's going to rotate, right? So complex multiplication is a way of generalizing rotation. And without going into too much detail about this, instead of thinking of a complex number as A plus BI, there's something called the polar form of a complex number, which instead of thinking of it as an X and a Y, it's thinking of it as a radius, how far out from 0 I am, and an angle. And there's a much nicer way of like multiplying those complex numbers. When I multiply those numbers, I just stretch the radii by each other. So if I have like one that's a radius 2 and one that's a radius 3, the multiplication is going to have a radius 6.
Mm-hmm.
And the angles are just going to add, right? So like it's literally just like scaling things and like combining the angles together. And that has like a nice geometry to it. But instead of thinking about it as like this imaginary thing that doesn't exist, it depends on your setting, right? Like when you're first
I feel like you just switched I just feel like you switched the definition a little bit. Turn the I into the Y axis instead of it being, I guess, the square root of -1.
But it is the square root of -1, because what does the square root of
The
-1
square root
mean?
of -1
It means something that when you square it, you get -1.
Right.
If it is the y-axis, and when I multiply by I, I'm saying I rotate by 90 degrees, then I times I is -1.
Right.
It's it's not the definition of complex numbers, but it's a geometric association. It's how you should visually be thinking of them. I mean, there's a lot more about them. Like why do we even introduce them? What are the settings that they're useful in?
Yeah. So I guess when would I be used? I don't know. You're a mathematician, so I don't know if you know about the real world, but when would I be used, I guess, in a situation in the real world?
Well, in the real world,
Or it never would be. It's just like waiting to be used if you multiply it by another I.
well, because you can't really think about like complex numbers without thinking of like this rotation.
You need it for complex numbers.
Yeah, I mean, if you want to be able to like rotate numbers in like 2 dimensions, like this is going to be the thing that you want to do. So anywhere in physics where like rotations show up,
You
like
can use I.
you could use I. You could do all of complex stuff with replacing I and making things look uglier with matrices.
Oh, really?
Yeah, there's a way of
I
going.
didn't know that.
Yeah, there's a way of viewing I. I believe it's the matrix 1. I think it's 1, 0, 0, minus 1. And it also has this property that when you square it, it's minus not 1, but when you square this matrix, it's going to be another matrix. It's going to be negative the identity matrix. So if you identify the identity matrix as 1, and when I square this matrix, I get negative the identity.
Right.
So you could do like all of complex like arithmetic using matrices and using just 2 numbers. I could call a complex number a plus bi ab and just have a weird multiplication on it. But that's like using the I notation makes it a little bit easier. You just remember that I squared is minus 1 and all of that is built into it. But to me, I think like the real application to complex numbers is maybe not a physical application, but it's just the idea that the complex numbers are the smallest thing you need to introduce to the real numbers to make every polynomial have a solution. So for example, x squared plus 1 equals 0, right? That's a very basic polynomial. You could try using your quadratic formula and you're going to get that the answer is I. You're going to get the square root is minus 1. But turns out that, okay, that solved that quadratic equation. If you want to solve any polynomial, having the complex numbers is enough. By just introducing
introducing I.
Just introducing I and the rest of the real numbers, you can now solve every single polynomial.
Wow. That's unbelievable. Well, Abe, thanks so much for joining us. I did not get to calculus. We didn't get to calculus. So unfortunately, I still have trouble with limits in calculus, but hopefully next time we'll discuss it. Thanks so much for being here. Really appreciate it.
Thank you so much for having me.
I feel like I learned a ton.
Me too.